This is our lecture on surface integrals. So surface integral is when we are trying to integrate over an entire surface in R3, or a surface in 3 dimensions. And what we're going to do is we're going to take that surface in 3 dimensions and try to subdivide that surface S into tiny little patches, each of size, well, ds. And remember, those patches, really, you can think of those as basically tiny little tangent planes. Then what we're doing is just taking a point from that tiny patch, evaluating it in our function f, and then we scale that result by the size of our patch ds, and then we sum. And so our surface integral is given as that, well, the double integral over our surface, evaluated at our function f, and then ds. Now just note that, again, this ds, it's actually a capital S because it is a capital S anytime we talk about our surface, whereas when it was just arc length or a curve, we used little s, which I know is kind of confusing, but I'm sure we all have wonderful handwriting, right? Shouldn't be an issue. Oh well. But the big issue with these surface integrals is that, well, my surface integral is a double integral, but typically my function, since I'm evaluating at every ordered pair in terms of x, y, and z, my function is 3 variables. And sometimes even my surface is 3 variables. So we need to parameterize. Most of this work we did back actually when we talked about parameterizing surfaces in that last lecture. And so essentially here's just the formula, right? We're going to turn our double integral over our surface into a double integral over the region D. Again, that region D being a region in just 2 dimensions. Our dummy variables are the variables u and v, although we almost never, or at least very rarely, actually use u and v. Typically, we're going to try to keep things in terms of x's and y's when convenient, or otherwise we'll convert to cylindrical coordinates, which would be r's, thetas, and z's. Again, hopefully holding one of those constants, so really just a combination of 2 of those 3 variables, or even sometimes spherical coordinates. One thing I want you to note, though, is that when we do substitute that ds, right, the capital S, that area of the patch, it's going to be the magnitude of the cross products of our tangent vectors, and then times the dA. So again, that's our scaling factor. That magnitude of that cross product is our scaling factor, or our Jacobian, to convert between ds and dA. And we're going to see that actually come up a bit when we talk about flux. So hold that into your memory for the time being. The special case where we're given a surface as z equals g of xy, and I know it's kind of confusing. We've been saying that for our functions of 2 variables, our surfaces in 3 space, there's always z equals f of x and y, but, well, the book changes it here because our function in our surface integral is the function f. So just be really careful that your book switches it up at this point, and I want to be consistent with your book that now at this point, any surface in R3 where we can solve for z, right? We have z isolated on one side of the equation, is now going to be given as z equals g of x and y. And so we talked about this parameterization in the last video. I can always parameterize my surface then as a function of my 2 variables x and y, and my x component is x, my y component is y, and my z component is just replaced with that surface, g of x, y. And then we make that substitution into our surface integral as well. And again, that scaling factor, that kind of Jacobian, is going to be then again, it's still that magnitude of that cross product, but we can kind of simplify things, and we know that it's going to be the square root of the partial with respect to x squared plus the partial with respect to y squared plus 1, where, of course, 1 would be the partial with respect to z squared, but that's just 1, and 1 squared is 1. And we use that formula. All right, so let's actually do this in practice and try an example where we're going to have to parameterize a few times. So for our first example of doing a surface integral out, our surface is actually going to be made up of 3 different surfaces in this case. So the sides of my surface are going to be given by the cylinder x squared plus y squared equals 3. So again, that kind of cylinder going around here. The bottom is going to be the disk given by x squared plus y squared is less than or equal to 3. And so, again, when we use the phrase disk, disk does mean that we are, well, integrating actually a solid region. Just not just the circle, it's going to be everything inside that circle as well. And again, the less than or equal to 3 also, well, helps us to understand that this is definitely going to be a disk, and we want the entire region on the inside. And then lastly, we have the top. And the top is given by the plane z equals 4 minus y. Except, again, well, to describe the surface, right, that's going to be that portion of the plane that's actually still bounded inside of my original cylinder. So, actually, this is really 3 examples in one, which makes this a really good one to do for you guys, because what we're going to have to do is actually look at each one of these sides individually. All right, so first we're going to have to do the bottom part, that disk. We're going to have to integrate that surface. Then we're going to have to do the sides, so then we'll integrate that cylinder. And then lastly, we'll integrate the top, which is that plane region. And each time we do, well, each of these surfaces individually, we're actually going to have to do a different parameterization with each one, which again makes this a great example. And so we'll do side 1, side 2, and side 3, and then put it all together to find out what the total surface area, surface integral, would be for this entire surface. All right, so let's start with the bottom of our surface first. Now again, this is what we're actually integrating. This is our surface integral. So for the bottom, again, I'm going to call this just side 1. So we're integrating over surface 1, or side 1. My function is y plus z, and then of course ds, right, for my tiny little patches. Now, to understand how we actually can take this, and of course the idea is that eventually I need to somehow take my surface integral and reparameterize so that I can actually integrate over just some region D, some two-dimensional region D. Well, this one's actually about as easy as it gets, because we know that this x squared plus y squared less than or equal to 3 is only in my xy plane. Well, if it's only in my xy plane, that means, well, z equals 0, right? And what I'm actually going to do is treat this surface as if it is just the plane z equals 0, that flat plane z equals 0, but my region D is going to be the circle. So again, I'm going to say z equals 0, which again, if I can set up my surface in that form, we use that g of x and y notation, because again, we're going to have to find some partials here. And then again, that region D is just going to be the circle in the xy plane. Well, of course, it is the filled-in circle. Right? It is that entire disk. So, well, we actually almost have enough to immediately make our substitutions and evaluate this integral. So, well, y becomes, well, y. That's not changing, right? Z is, well, what's z? Well, I literally just defined it to be my plane z equals 0, so that's gone. That's gone. Now, the beauty of this one is that, again, I could set this up as a plane as my g of x, so my ds is going to get replaced with that big square root of my partials squared, summed, and, you know, including 1, and then my dA. So, well, now I need to find my partials, but these are quite literally going to be the easiest partials you ever calculate in your life, because if my function is just 0, my function g is 0, well then partial g with respect to x is 0, and partial g with respect to y is also 0. So it's going to be 0 squared plus 0 squared plus 1, which is just going to be 1, and the square root of 1 is 1, and multiplying by 1, well, it doesn't change anything. So all I really need to do now is actually evaluate what is y dA going to be over my region D. Well, my region is a circle, so let's actually parameterize this with polar coordinates. So for polar coordinates, well, theta, it is the entire circle, so theta is going to be bounded from 0 to 2 pi. And then my radius, again, I want this entire disk. So my radius is going to be bounded between 0, because again, we're including the entire thing, all the way out to the outside. Well, what's the outer radius here? It's the square root of 3. Be very, very careful, right? It's always the radius squared. So, if it was 3, my radius goes up to the square root of 3. So, now I just, well, make my substitutions. Like I said, we know that this entire radical part is just 1. And so, turning this into a polar coordinates, right, double integral over my region D. So integrating, so 0 to 2 pi. And again, I'll put my d theta there at the end. Then integrating from 0 to root 3 for my r. So there's my dr. And then, well, replacing y. Well, we know from polar coordinates that y equals r sine theta. And then here's the big one we don't want to forget, right? That dA. When I switch to polar coordinates, remember that dA is really r dr d theta. So again, make sure that you're really, really careful. If we're substituting in terms of r's and theta, we do need the r dr d theta when we replace dA. So we're going to end up with an extra r, which means this is really going to be r squared. And the nice part is we can kind of actually factor all this, and well, this shouldn't be too bad of an integral to actually evaluate, because you're going to integrate r squared with respect to r, so 1/3 r cubed, plug in the bounds, and you integrate sine. The integral of sine is, well, negative cosine. But here's the part. When I integrate, right, that sine function, I get, well, negative cosine. When I plug in my limits of integration, when I evaluate my upper limit, 2 pi, well, cosine of 2 pi is 1, so that'll be negative 1. But if I evaluate it at 0, I'm also going to get negative 1, so it'll be negative 1 minus negative 1, which is 0. But I'm then multiplying it with whatever I got with r, so it's going to be 0. Wait, this entire thing, and again, you don't understand what I'm saying, go through and actually do the integration yourself. My answer is going to be 0. Just 0? Right, the whole thing becomes 0. So when I integrate over the bottom of my surface, my answer is 0. Now, here's the thing. This should hopefully make a little bit of sense as well when we look at what we're actually integrating. So I'm integrating over the function y plus z. Now, like we said, we already showed that the z is gone, right? That's gone. So all we're really evaluating is going to be y. Well, when I drew my region, it's symmetrical. It's symmetrical about that line y equals 0. You have the plus, and you have the negative, and yeah, when you plug in every single ordered pair, they're going to actually end up canceling out. Everything should cancel out. This should intuitively be 0. Now again, if your intuition isn't there yet because, oh, you know, this is your first semester doing vector calculus and doing double integrals, that's fine, right? Do it out. Do the math out. But try to see as you do the math, and again, it's really going to be, you know, that one right there, because we're going around the entire circle, which means we're doing, well, the entire disk. That's going to be the reason that this part becomes just, well, 0. But this is the easy one. So I guess it's time to actually do one of the harder ones now. Alright, now it's time to do the sides of my surface. The sides of my surface being that cylinder, x squared plus y squared equals 3. Now, it's a cylinder, so hopefully we recognize that probably using cylindrical coordinates are going to be the route that we really want to go here. Again, x equals r cosine theta, y equals r sine theta, z equals z. But again, the issue is, right, my surface integral here, what I'm trying to eventually do is write this as just a double integral over region D, if I can. And that double integral means, well, only 2 variables. But I have r's, thetas, and z's. But the nice part is, again, we know that we must, well, keep that true, which means, that's the case, r equals the square root of 3. And so our parameterization, x equals root 3 cosine theta, y equals root 3 sine theta, and, all right, well, z equals z. And we still only have our two variables then, thetas and z's. And because we now have it in terms of just thetas and z's, I can now actually parameterize my function and my vector function r now as a function of theta and z, where now we have our I hat component, our j hat component, and our k hat component. But our I hat component is x, so that's root 3 cosine theta I hat plus, and then my j hat component would be root 3 sine theta j hat plus, and then just z k hat. So now we have all of our component functions. That's our parameterization. And now, well, to actually set up this integral, what I have to do is actually now take the partials of, well, my parameterization with respect to each of the individual variables that I chose. So I'm going to take the partial of r with respect to theta, and then the partial of z with the partial of r with respect to theta, and then the partial of r with respect to z. So we're going to get those two partials. Now, here's a good place for you to pause, because I'm not going to go through it, because it's not too bad. Figure it out on your own, and then unpause the video whenever you have your answer. Alright, now that we've defined our function, and hopefully you took those partials yourself, the partial with respect to theta gives us negative root 3 sine theta I hat plus root 3 cosine j hat plus 0 k hat, because the derivative of z with respect to theta is, well, a constant, which is nothing. And then the partial with respect to z would be 0 I hat plus 0 j hat plus 1 k hat. Now, what we're really trying to do, of course, is when we try to make our change here, right, we got to replace our ds with the magnitude of the cross product of our partials, dA. And that's really the purpose why we're doing all this stuff with the partials, which means the next step is to calculate the cross product of these two partials. And again, use any technique you'd like. Right, the book sets it up as this minor matrix. But again, I'm going to give you a second, pause the video, calculate that cross product, and then unpause when you're ready. Alright, did you calculate that cross product? The result you should have gotten would have been negative root 3 cosine theta I hat plus root 3 sine theta j hat plus 0 k hat. And then we want that magnitude. So again, magnitude means we're just going to take the square root of each of those components squared. So again, square each of those components, sum them, take their square root, and this one should simplify fairly nicely to root 3. Which means that when we make our substitution, we're trying to set up our double integral, it means that this ds is really going to become root 3 dA. And in this case, dA is going to be, well, my two variables in the problem, which is theta and z, which means a d theta and a dz. But, well, I guess what we need to do next is, if it's in terms of thetas and z's, well, I need my bounds for thetas and z's. Now, if you need to, go back and kind of refer to that first picture, right? What does the surface actually look like? And so for my bounds, well, theta is pretty straightforward, right? It's the cylinder all the way around, which means theta is going to be bounded between 0 and 2 pi. But the other part, z, well, let's see. Z, well, again, if you look at the picture, we know it's bounded on the bottom, right, by my disk, which is z equals 0. But on the top, it's bounded by the plane 4 minus y. So that'll be my upper level, my upper limit of integration, except, wait, I can't just introduce any brand new variables that I want into here. I can't just use y. I'm going to have to, well, substitute y for what we know y to be equal to. So my upper bound for z is actually even going to become 4 minus root 3 sine theta, which is what I'm going to have to plug in. Now, which also means that right, when I set this up, even though I put d theta first and then dz, well, z is in terms of a function of theta, which means when I actually set up my integral, I'm going to have to swap these two. I'm going to have to integrate with respect to z first because, again, z is bounded by something with variables. I'll do theta last because theta is bounded by just constants. And again, anytime we set up a double integral, our last integration is going to have to be, well, whichever one is just constants. So, let's actually take a second to write out what this entire problem is going to be. Now, also, right, we have our y plus z up here. Remember, we're going to have to substitute for this y also. So, in my integration, y becomes, well, like we said already, root 3 sine theta, then plus z, then times, and ds becomes root 3 dz d theta, and those are our bounds. So let's do a little bit of integration. And I'm going to clean this up first. Be right back. Alright, so the double integral we have now, the integral over my region D, which is defined in terms of z's and thetas, and that root 3 from my, converting ds, that's a constant. I can factor that all the way outside, so I'll leave that on the outside no matter what. Again, my outer bounds are the ones in terms of theta, so again, I'm going to basically just bring those down, right? I'm not going to worry about integrating with respect to theta. I just now need to look at my integrand with respect to z. All right, and again, those limits of integration would be from 0 to the 4 minus root 3 sine theta. Now, notice this root 3 sine theta that ended up inside my integrand. Am I going to be able to factor this? Well, no, I cannot factor this. Remember, this is a sum, and I cannot factor with sums, right? So I am going to have to leave this here. I can't factor it out because it's not multiplication. It's not a product. It's a sum. So I am going to have to actually integrate this entire thing. But I do treat this whole root 3 sine theta as if it were a constant. And so what's the antiderivative of a constant with respect to z? Well, it's going to be that constant. So root 3 sine theta times z, right? Just like the antiderivative of 2 would be 2z. The antiderivative of root 3 sine theta is root 3 sine theta z. Plus, and the antiderivative of z with respect to z, well, that's just going to be 1/2 z squared. And then we need to evaluate the entire thing from 0 to 4 minus root 3 sine theta. And that might require a little bit of work on the side. Now, the nice part is, when I plug in my bottom limit of integration 0, 0 and 0 squared is still just 0. So, again, plugging in 0 is going to be easy. All I really have to do is worry about what's going to happen when I plug in my upper limit of integration. So again, I'm going to do that as a little bit of scratch work here. Alright, so when I plug this in, so root 3 sine theta times, and my z is 4 minus root 3 sine theta plus 1/2, and then z squared. Well, z is that entire quantity, 4 minus root 3 sine theta, and the quantity squared. And what I'm going to have to do is, well, clean this entire thing up, which is going to require a little bit of work. So, first, I'm going to have to distribute. For that first one, right, distribute through my set of parentheses. And for this one, to expand the square, I am going to have to go and actually write it out and FOIL the entire thing. So, practice some of your algebra skills here and simplify this. And pause the video, wait till you actually simplify it, and then come back and see if you get the same thing that I got. Ready? Go. Alright, did you do the algebra? So the first part, we should get the, well, you're just times it by 4, right? Distributing by 4, so 4 root 3 sine theta. And then when we multiply the root 3 sine theta times root 3 sine theta, well, that gives me, well, minus 3 sine squared theta. Then when I expand it to square, so 1/2, and then the square would be 16, so minus 8 root 3 sine theta plus 3 sine squared theta. But I still have to distribute through that 1/2. So when I distribute through that 1/2, well, clearly 16 just becomes 8. I distribute through that 1/2. This becomes 4 root 3 sine theta minus 4 root 3 sine theta, which, well, that's kind of nice, because that is going to cancel that. And then over here, when I distribute that through, again, one last time, so plus 3/2 sine squared theta. Well, let's see, what am I actually left with? So I have the 8, and then minus 3 sine squared plus 3/2 sine squared is going to be minus 3/2 sine squared theta. And that's what my integrand is going to be now when I do this with respect to theta. So again, I'm going to bring this back. Now I'm integrating from 0 to 2 pi. This expression with respect to theta. Well, I'm going to have to do something here. Because if I want to integrate with the sine squared, I'm going to have to use my power reducing. So, for this, to evaluate this integral, we are going to need the power reducing for sine squared. And so, what's the power reducing for sine squared? Oh, you thought I was going to just tell you? No. Either you have it memorized, and that's good, right? And you'll be able to check your answer in a second, right? Because of the video, right? And you can't really stop me, right? I'm just a video, not actually your instructor, so. But you should. If you remember it, that's awesome. Substitute. If you don't remember it, pause the video right now and go and look it up. Don't have me just tell you what it is, because there's no actual learning involved there. You're going to see that power reducing come up a bunch, especially in all these types of problems. And so make sure you have it memorized. All right? So pause the video, and I'll be right back with the simplified form for us to integrate. Alright, so it took a second to kind of clean it up. The power reducing for sine squared is the 1/2, 1 minus cosine of 2 theta, right? Going back to our double angle formula. So I already have 3/2 in front of the sine squared, so that extra 1/2 makes it a 3/4. And of course still the 8. So 8 minus 3/4 times that whole quantity, 1 minus cosine of 2 theta. And again, going back, right, this is the original integral we started with after, all of this work that we've done. We have that root 3 as a constant that's still factored outside. We're integrating theta from 0 to 2 pi. And again, this is the expression we have left. Now, before we actually integrate, let's clean it up one last time here. So root 3 integrated from 0 to 2 pi. And what I really want to clean up is the constant. So I have the 8, and then minus, well, when I distribute this here, minus 3/4. So 8 minus 3/4, so that's 32/4 minus 3/4, so 29/4. And when I distribute through the minus minus, so that becomes plus, and plus 3/4 cosine of 2 theta d theta. Alright, now I need to integrate. So this part here, well, I'd have to use a u sub, right? I can do each of these separately. This part would definitely require a u sub, where my u would be 2 theta, which means that du would be, well, 1/2 d theta, except that's not even going to matter, because when I plug in 0 and 2 pi, right, it's going to be a trig function, right? When I plug in 0 and 2 pi, it's going to be the same value, right? Whether it's a double angle or not. So if you see it, that's great. That part's not going to matter, because it's going to end up canceling itself out at the end. If you don't see it, again, that's fine, right? Actually write it out, do the problem, and then see how, well, when we get to the actual end of the problem, then you'll see how it cancels out. But again, if you recognize these things ahead of time, you're going to see the same patterns cropping up over and over and over again. You can make your life a little bit easier now, right? You're almost done the calculus sequence. Again, the more you do these integrals, the more intuition you'll get. You'll see the same things happening over and over again. And again, I've done hundreds, probably thousands of these types of integrals. So again, I can see immediately that I know it's going to cancel out because I've done enough problems that my intuition is there. If your intuition isn't there yet, well, yeah, again, it's your first semester doing Calc 3, so I think that's all right. However, if you don't see it, then do it out. Do the problem out. You're not going to get better at this. You're not going to gain any intuition if you don't actually practice it, right? Math is this very kind of great subject where you don't get better unless you practice it. But every time you practice it, you get better. So, yeah, see how that works out. But the nice part is, again, I recognize at this point that that's going to go away, which means I'm just left with the 29 fourths. And, well, what's the antiderivative of 29 fourths with respect to theta? Well, 29 fourths theta. That's it, right? It's constant. Don't forget we still have that root 3 out front. And I'm evaluated from 0 to 2 pi. Well, obviously 0 is going to make the whole thing go away. And I plug in 2 pi. So 2 pi, well, if this becomes 2 pi, then well, I can kind of simplify my fraction there. So it looks like I'm going to have root 3, 29 halves, pi. Or I should probably clean that up a little bit. 29 root 3 over 2 pi. And now that is the value for my second surface integral, which is that cylinder around the outside. So that's 2 down, 1 more to go. Now it's time to do the top. Alright, time for the last side of this surface, which is going to be the top. Now remember, the top of the surface was that plane defined by 4 minus y, which is really nice because z equals 4 minus y. It's that z equals format, so we're really going to let it be the g. Right? We'll let it be my function g, which means, again, when we replace this ds, we're going to use that, well, formula that involves our square root. But before I can do that, I got to calculate the partials. The partials in this case are going to be, well, not 0, so this will be slightly, well, a very slight amount of work more, but, yeah, so g is the function 4 minus y, so the partial of g with respect to x, keep my lowercase, is, well, 0. And then the partial of g with respect to y, well, 4 is a constant, that's gone, so the derivative of minus y with respect to y is minus 1. So now that I have my partials, again, the whole idea is to put in that square root function, so square plus square plus 1, but, well, negative 1 squared is 1, 1 plus 1 is 2, so it looks like this is just going to be the square root of, well, 2. So, let's go and actually try to turn the surface integral and convert so that we can integrate over my region D. And in this case, my region D, well, it's going to be the cylinder that encloses this top portion of my plane. So let's see. Well, so we have y plus z. But again, I don't want to do this in terms of z, right? The whole idea is I'm getting rid of my z so that I'm doing this in terms of x's and y's. But we know what z equals. Z is 4 minus y. So y plus 4 minus y. The ds becomes, well, the square root 2 dA. But what's going to happen here? So let's see. Well, y minus y, that's going to cancel out. So it looks like I just have 4 times root 2 as my integrand. But those are constants. I can factor that out. So 4 root 2, and then the double integral over the region D, dA. But remember this, when I factor everything out, right, when it's the constant function, when all that's left is, you know, like that invisible 1 here, remember this whole part is equal to the area of that region D that we're integrating over. But we said that region D was the cylinder, right? It's that circle where we had the radius was equal to the square root of 3. Well, what's the area of a circle with the radius of square root of 3? Well, area equals pi r squared. So the area is just going to be 3 pi. Bring that back over with this constant. And it looks like my answer is going to be, so 4 times 3, so 12 root 2 pi. That's my last side. Now, that means my entire surface integral. All right? An entire surface integral, adding everything up. We add up the first side, right? The bottom, the one we did first, which was 0. Plus the second side, the cylinder, the outside one, right? The real beast of a problem, which was, what, 29 halves root 3 times pi, plus now 12 root 2 pi. And again, there's no good way to simplify it, so you're just going to have that big, long, kind of messy expression. And that is the answer to this surface integral.